what we left. So I will share my screen and go back to the presentation, the point we left the discussion. Okay, how do I do this while I'm online? Share this one. Just, can you confirm you can see the screen?
Yes, we can see.
Yes.
Thank you. So, I don't know if you remember, last time we started to present what I refer to as a heuristic presentation on what, when we estimate the parameters of the Rush model, what do we do? So how conceptually we process the information. And just to remind all of you, the information that we have is in a form of a matrix of simple data, 0 and 1. So this is, in my terminology here, I'm calling X. X are my data. And they correspond to 1 if a certain person said yes to a certain question, and 0 if that person said no to that question. What we are interested in eventually is this parameter A, which is, in our interpretation of food security, the position of the respondent on a scale of severity that goes from one extreme, let's say low values means people are food secure. High values, the other extreme, means that people are severely constrained in their access to food, to the point they will probably not have enough food to eat, they will have malnutrition, they may even face serious death risk and starvation. So these are the two extremes of what we assume is a single unidimensional scale of severity. So it's something that we can actually measure on. So having said that, my heuristic presentation illustration of the Rush model has two purposes. One is to test your ability to understand what is the rationale behind the Rush model. And so why it makes sense that we can use responses to these questions to determine what is the most likely position of a respondent on this scale of severity. But the second one is also to give you a hint into what doing maximum likelihood estimation means. So I find this exercise quite useful, and that's why I keep using it. So last time we started by saying once you have the data, we can start looking at the data from two different perspectives. One is, let's try and understand what difference exists between the items, so these columns. And to make an assessment of the difference between the items, we exploit the fact that we have 1,000, 2,000, 3,000 respondents. So we look through the data by column. And the first thing that we discussed is that conceptually, in a given situation, in a given population, if something is reported by more people, if something is more frequent, that means it's probably a relatively mild condition. It's something that occurs often and it's not very dangerous. And therefore, we said the first piece of analysis is we can rank the item in an order of severity, in our candidate order of severity, by looking at the percentage of responses to each question. And so the first lesson is that we don't impose the severity level of the item a priori. We obtain the severity level of the item by analyzing the data. And in this example, we found that the order would be question 1, then 3, then 2, then 4, then 6, then 5, then 7, and 8. And this is by looking at the share of the respondent who said yes. And here it's an example that demonstrates that in this application there was quite good discrimination, because there is a quite wide range going from almost everyone saying yes to the first question, only 20% saying yes to the last question, which means that there is it's a well-designed test that scans a large range of severity. And so I draw this line on the top of the chart to just remind you that this is what we want to do. We want to try and locate this item on our scale of severity. And then we want to also locate the individuals, the respondent, the households. So we started now changing the perspective. Now, instead of looking at the data from the column perspective, let's look them from the row perspective. And this is the key now on giving you an idea of how the information is processed. So we look at the first respondent. And we say, we know what are the responses. This is our data. And now we want to try and guess of all possible values of my parameter A, of all possible position of this respondent along the scale of severity, which is one that is more consistent with the data that we see. Which position makes this particular sequence of response the more likely? And this is the question I asked you to try and guess last time. And more or less, this is where we were. So let me ask again, and feel free to either take the floor, unmute yourself and give, or let me put this chat on the screen so I can see if you type your response here. So if we look at respondent number 1, who said yes to the first question, yes to the third, yes to the second, yes to the fourth, yes to the sixth, but no to the fifth, to the seventh, and to the eighth. So this is our information set. And now let's imagine, if this were a person that is very food secure, is located here at the beginning of the scale, would this be a likely pattern of response? Well, somebody here clearly will probably say no to the very severe question. Remember the Rush model, the distance is very large. If the person is here, the distance to question 8 is very large, is a negative number because A would be lower than B. So maybe one thing I can do is see if I can do this easily. In a way, it's like looking at the column. I have a first indication of what the B parameters I. So now, and this is complicated because I'm doing it with my mouse. So this would be B8, sorry for that, B7, and so on. No? So I do have positioned my items, but now I want to position the responder. And what if A1, so the position of the first respondent is here. If that were the case, I can understand this answer no. I can understand this answer no. I can understand the answer no. But this answer yes start to be very problematic. The model would predict that if there is this distance from B6 to A1, this large negative distance, the model would predict a number that is very close to 0. So the probability of observing one conditional on the position being this far, it's very low. This is an unlikely result. Okay? So now the logic behind the maximum likelihood say, okay, then I to say A1 is not a reasonable position. And you could try and do your mental exercise of evaluating different candidate position, and then in your judgment, what would be the maximum likelihood estimation of A1? What is the position that would make the observed pattern of responses the more likely? And let me ask this question again. So any guess, any intuition? Don't be shy. This is helpful for everyone because it helps me to understand whether the presentation is clear or whether the particular issue is very problematic or not. So don't be shy. Okay, so I have Stefania writing between 0.65 and 0.52, which I refer to this percentage of positive response. And the answer is correct in the sense that it is a position between the severity of 6th item and the severity of the 5th item. So let me put the pen again. This would be B5. And Stefan is saying should be somewhere between here. And Stefania, can you tell everyone what is the reasoning that you made?
Okay, what I suppose is that the position is here because until question 6, he answered yes. And question 5 is the first 0. So I think that his position could be placed in the middle between question 6 and question 5 average.
And the reason is because according to the theory behind this model, according to the expression of the Rush model, if what Stefania says is true, the probability of having observed this sequence of response is the maximum, is the highest. This is the most likely pattern of response for somebody that is positioned here. And that is absolutely correct. Does anyone has any doubt or question about that? Is it clear to everyone? I don't see many faces, I only see a few, but please don't be shy and tell. Okay. So let's assume now that this is clear. And so the next slide, I put a thick red bar in the position for each respondent. And now I'm asking a difficult question. Look at individual number 1 and individual number 6. And I am putting the same position to both, even though the pattern of response is not the same. What do they have in common? The only thing they have in common here is that the total row score is 5. And now let me announce this is a theorem that if data is conform to the Rush model, if all items discriminate equally well across respondent, so if this item response function are sufficiently close to being parallel to each other, then the row score, which is a synthesis of the data, is a sufficient statistics to estimate the respondent parameter. So I don't need to know which question has been answered positively. I only need to know how many questions have answered positive to estimate the respondent parameter. And now this seems a little bit strange. This seems a little bit complicated, obscure, and why? And so now the next step in this heuristic presentation is to try and illustrate why is that, and so indirectly also to give you an explanation of what does it mean to have a sufficient statistics. So now let's look into the detail of the pattern of responses of the 6th respondent. And now let me take advantage of Stefania again to guess the right for the first case. Now, what is strange about the 6th respondent if indeed the respondent is located here?
Sorry, I didn't hear very well the question.
Ibrahima, the question is, if this guy have responded yes, 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 no, yes, yes, no, no, and I am claiming the position of this respondent is here, the same as the first one, what is it that is strange in the pattern of response? What do you note that it's unexpected? It's something that seems to violate the theory that we exploited that Stefania exploited to claim that the best guess, the position of number 1 is here, because he said yes to all less severe question and said no to all more severe question. Here, there is something strange. What is it that is strange?
Yeah, I think.
Go ahead, Ibrahima.
Yeah, I think the fact that we have a positive response at Q5 is unlikely. And
Yeah.
at the same time, also the fact we have a negative response at Q4 is also unlikely.
Very good. Indeed, that is what's going on here. That if this is true, we would have expected no here and yes here.
Yeah.
So now just for the next step, I have highlighted with a yellow background and a red color the unexpected responses. But now let's imagine, okay, there are 2 responses that are unexpected. But what do we do with this information? So here again is the way in which we process the information to come up with our response. And so let me help here and say, well, because this guy said no to a question that is relatively mild, I would like to pull this position more to the left, because I have some information. Remember, this is a key result, and I don't know if Veronica is still with us. Veronica Boero and I were in a workshop in Panama or in Mexico, I don't remember where, with Mark Nord, the person that contributed the most to make the food security measurement based on the Rush model more popular. And he revealed a very important consideration that I find it very interesting. In the Rush model, both yes and no are answers that provide information. And therefore, we need to carefully evaluate both. What does it mean if somebody has said yes? But also, what does it mean if somebody has said no? Because these are 2 pieces of information that contribute both to determine the inference. What we are trying to do is an example of statistical inference. From the data, we want to derive an information on the characteristic of the respondent. We want to infer what is the position given what we know, which is the data. So this no answer, Ibrahima said, this is strange, because if the person were here, it would be very unlikely to have no. So this person should be to the left, possibly here or before. But at the same time, he said yes to a more severe question. So I would like to pull it in the other sense. And this is what seems magic about the sufficient statistics, the Rush model, is because these 2 effects compensate each other. So the combination of these 2 strange results bring me back that if I have to guess what is the most likely position of this respondent, it must be here. But now, a more difficult question then. But then, are these pattern of response the same? No. but they lead to the same parameter estimate. So what's the difference? What is that makes this estimate different from this estimate? Any guess? And don't try to be technical, just the conceptually. Let me put it in a different way. I think you are very shy. Are you more confident that this is a good assessment or this is a good assessment? Which of these two are more precise, are more trustworthy, are more reliable?
The estimation for the individual one?
Correct. Exactly. So there is a difference between these two, and that I am more confident that I got this right. Here there is some residual uncertainty.
Yes.
That because of these two strange responses, I'm not very confident. But there is nothing I can do because this is a statistical assessment. And I have to recognize that there may be measurement errors, that there may be uncertainty associated with my final assessment. And you are seeing it now. Okay? And now, let's now look at again at the entire matrix of data. And here I have highlighted all the cases that are strange. And I want to make some claims that some of these results are more strange than others. And the claim is that, first of all, you will notice that the position, the red bar, is determined just by the row score. If row score is 1, the position will be here. We have no case. If row score is 2, the position here. If row score is 3, the position here. Row score 4 is here. Row score 5 would be here. Row score 6 would be here. Row score 7 would be here. No? This is the sufficiency of the row score. Given the row score, I know how to classify them, how to position them. But then, some cases, the strange response are very close to the position of respondent, which means that yes, I would have expected, for example, yes here and no here, but the distance, it's relatively small. So I am, if I go back to this chart here, the difference between A and B is around 0. It's a little bit to the left, a little bit to the right, but I'm in a range that in any case, the probability is close to 0.5. So yes, it was more likely to have a no instead of a yes, but this more likely is not so strong. It's like 60%, 55%, as opposed to 45 or 40%. Whereas if you have some errors that, like, I don't know, I could say this one that is quite far away, or even this one that is very far away. These are cases that the result is very, very strange. So I want to say that the errors become more relevant, more intense, the greater is the distance between the estimated parameter of the respondent and the actual response. So first consideration, not all measurement errors are the same. Not all unexpected responses are equally strange. Second, look at the column now. And there may be cases in which, and I'm just inventing number, that if I look at the column in the economy of the entire sample, in this question there are too many unexpected responses. This question is not working consistently with what I would like to, what I would expect if the Rush model theory was true. So this is the basis for testing whether the question belongs to the scale, whether I should keep it as a contribution to the measurement, or it's dangerous because people are responding to this question in a way that is inconsistent with what I would expect given all the other responses. So a case like this, where a question have too many unexpected response, or that have responses that are very far from what I expect, so that imply a very large error, must be questioned, must be dropped from the analysis, must be considered not suitable for this measurement. So this is the basis, heuristically again, just from a purely logical reason point of view. How is it possible that with just a matrix of 0 and 1 and an underlying theory, we can perform an estimation and statistical tests? Okay, let me pause now for a moment. Let me stop. Let me ask you if you have any question or doubt. And then BlackBerry. Oh, Babadi, what will be the case if individuals say yes for Q8? Will be this individual dropped? Can you clarify, Babadi? What do you mean?
Yeah, I mean that for all these questions, if the individual says no from quiz 1 to quiz 7 and it says yes for Q8, and we will have a lot of irrelevant answers. So how we can treat these individuals?
Yeah, you are absolutely right. There is an opposite example in the table, is this individual here, which have said yes to all questions, but say no to the first one, which is symmetric to what you say. You are saying something like the last one. I said yes almost to everything, and then no to the last one. So, first of all, if you say yes to everything and no to the last one, is not a problem. But if you say no to everything and then yes to the last one, this is very strange. So two things may happen. One is that, remember, we only see the numbers that somebody has typed in the data. So the first thing I would do is say, let's go back to the questionnaire. Is this a mistake? How is it possible that somebody said yes, say no, I'm not worried about food. No, I don't skip meals. No, I don't reduce the amount. And then yes, I go for an entire day without eating. That's complete nonsense. So one possibility is that that last number is wrong. But before concluding that, you better go back. If you have the questionnaire, you look at the questionnaire and check that this is not a coding error. If you don't have any evidence that this is a coding error, then you have to say, okay, this respondent is too strange. And so I probably better drop it or treat as missing. And then you continue. And if you have too many cases like this, you have to say my data collection went wrong. Either the enumerators are not actually asking this question, they're just filling in numbers by random and throwing to me. But you see, this is so important because now you start understanding how the data themselves, because we have a reference model, can help identifying these strange cases. And again, this is the basis for testing the Rush model. But if you don't have the Rush model to make sense of the data, you cannot do these tests. So let me again take the opportunity to mention, if you think of other proposed food security indicators that are also based on collecting some data, scoring them, and then classifying based on the score. How do you check whether your data makes sense or not? Unless you have a reference model, the question of validity and reliability cannot be answered. And this is what I have seen so many times, that people collect the data, don't question them, and present the result as if there was no uncertainty, there was no measurement error, there was no problem with the data. And this is wrong. This is absolutely wrong. This is deontologically incorrect. This is a mistake. So the basis for making this assessment is a reference model that allows you to characterize the measurement errors. With the Rush model that applies to many areas in which your data is just dichotomous yes or no, or can be also, we will cover it later, can be also frequency, you can form residuals, errors. So what I have now on the screen is that now you have run the software, you have estimated the maximum likelihood value of the parameter A and B. This is what the little hat on top of the letter means. So these are not just possible values, these are the estimated values. And if you have the estimated values, you just plug them into the formula and you can calculate the expected probability for individual I to say yes to respondent to item J. So every cell in your table, you can have an equivalent table in which instead of 1 and 0, you have the expected probability. So this will be a number between 0 and 1 that you calculate by simply applying the logistic formula. Okay? Then, what if I now compare the actual response? This is the data. It's either 1, meaning yes, or 0, meaning no. I compare the actual response with the expected probability of yes, which is what I just calculated. Now, what may happen? I observe yes. So xij is equal to 1. And my model predicts a very high probability of saying yes. So Pij is very close to 1. Then the error, the residual, the discrepancy is very small. So for all black cells, this will be very small. But there may be cases in which I see yes, but my model would predict no, like in this case. I see yes, but my model would predict no because somebody here would likely say no. So in this cell, I will have 1 minus a very small number, close to 0. So this will be a large error. Okay? Does this make sense? Now, Bobadi is asking another question. Should other items J should be included as control variable in estimation of the logic model? Bobadi, this is don't take it wrong. It's a little bit of a confused question because you are mixing two different things. First of all, I have never spoken of logit model. All along, I have spoken about logistic function. So
Sorry,
first,
logistic.
yeah, but I mean, it's important, it's good, and I appreciate your asking this question. But there is some confusion between what we have been talking so far, and there is another important econometric model, is called the logit model, in which you try to explain what is the probability of saying yes given a number of other variables. And so behind your question, there is a very deep, good intuition that you could frame the Rush model as a logit model. But that's not exactly what I have been doing so far. But yes, you could see this in terms, if you are familiar with the logit model, you could say, what if I estimate a logit model in which I want to explain the probability of saying yes to what? The probability of saying yes to the first question? Because here you would have 8 different logit models, right?
Yes.
Probability of saying yes to the first question as a function of all the data. Probability of saying yes to the second question as a function of all data. These are 2 different models. The Rush model embeds all of this together. So it's the most efficient way of using this information. And this is what you will find in the book by Bond and Fox. That is why they claim the Rush model is the only model that makes the most efficient way of the information, or use of the information. Because you could get to similar results by applying different combination of models. In the Rush model, you have all of this together. But let's go back to the question of, do you understand now what is this residual, no? is an estimation of how big is the measurement error. For each data point, for each question, for each respondent to each item. And so what you can do is by analyzing these residuals, you can create statistics, tests. And one very important is the in-fit statistics. That is a statistics that allow you to determine whether you should keep the question, because overall the combination of error is relatively few, and those few are relatively small. Or you have to drop the question. If there are too many, or if there are some that are very big, you have to drop it. And going back to another question that Ibrahima asked, you can have in-fit statistics also for the respondent. So you can identify which respondent is very, very suspicious. And so you can go back, see the questionnaire and see whether there are coding errors, fix that error and rerun the analysis. Or you can drop. Or you can try and see whether or not there is one particular data collector, one enumerator, that is associated with many strange cases. And then you want to question whether you should pay that person or not because they didn't do a good job. No, there are many ways in which the information on which cases are unexpected, are strange, are suspicious, can be used to reevaluate your data. Okay, now I see another question from Stefania, and this is a good question. Is there a standard value for the error according to which you decide to keep or drop a data point? And the answer is yes. So let's move. You are anticipating what would be the next. So applying the Rush model to food insecurity led to the development of the food insecurity experience scale. We have 8 questions. But these 8 questions are just the standard items that we use. Nothing in principle prevents from imagining additional questions, other questions that follow the same logic. For example, in some cases, people have been asked, have you lost weight because you couldn't get enough food? Or have you ever been borrowing food? Or have you ever stolen food? Or do you look for food in the dump, in the garbage? No? These are all potential things that could reveal a very difficult situation. Sending children to beg for food, going to some other household to try and get food, you know. This was very common in my own culture when where I come from, in which I heard old people making the story, telling the story that when things would become difficult, they would say to their children, go to this neighbor, the friend, and see whether they will invite you for lunch because I don't have any food to offer. No? There are many strategies, many things that people can do. And so some of these might be used as additional question in a questionnaire. What I want to say is that because of the theory, because of the possibility of testing whether the question belongs to the scale, you can ask more questions. Because before using them, before concluding that this is an improvement, you can test. And so the only cost would be that you have spent a little bit more time and more resources in collecting the data, but potentially this is an improvement of the precision, because the more question you have, the more precise you can be in your classification. But let's continue, because I think Stefania is a very important question. So in the presentation, you find a little bit of the history behind the FIES, how it was developed, and some of the considerations that are necessary to understand when you apply it. But I want to going to the I think I have the protocol to follow when you have the data and you want to compile your assessment. For example, this is a presentation that I developed to inform the calculation of the SDG 212 indicator. But the principle, the protocol is the same. If you want to use the FIES in the context of a resilience assessment, then you need to follow more or less the same protocol. If you want to use the FIES data in the context of an IPC analysis, the analytic protocol is the same. So what do you do? First, you have to make sure that you have the right coding of the answer. So if the answer is yes, you put 1. If the answer is no, put 0. And everything else is missing. So this is a good observation. It's a good practice to always give the possibility of people to say, I don't know, or to say, I don't want to respond. Because, as I said, yes, provide information. No, provide information. I don't know, doesn't provide any information. One of possibly the most common mistake I have seen by people, for example, preparing a questionnaire, is they say, this is a dichotomic question, yes and no, so I only need one checkbox. I check it if yes, and otherwise I leave it blank. But if you leave it blank, is it no, or is it I don't know? Is it no, or is it missing? And so this would be a mistake. You need to have at least clearly the two options and the instruction. You need to check one. And if there is no clear yes or no clear no answer, you leave it blank. Or even better, to have the option to check also refuse to respond, don't know, missing. Then, once you have the data, you estimate the Rush model. At next lectures, we will go through the software, and we do it. Yes. Then you look at the in-fit statistics, which is one typical outcome of the estimation. And Stefania, here is your answer to your question. The in-fit statistics, from a technical point of view, is like a chi-square type of statistics in which the ideal value is 1. But you can be more or less distant from 1 and still be acceptable. There are tabulated data, and the experience and practice in using the Rush model suggests that if the in-fit statistics is lower than 1.2, this is an excellent result. If it's below 1.3, you can still keep the item because it will contribute to measure without biasing the result. But you want to look at the question, let's say how it's been asked, because there might be some confusion on the way in which people have responded. So between 1.2, 1.3 is a sign that possibly the item can be improved. But if the in-fit is larger than 1.3, you have to drop it. And then there are other things that we will cover in the next episode because it's already 2 minutes to 2 o'clock and I need to leave to join my next meeting. So once again, apparently we didn't do much, but I encourage you to look back at the presentation and what we said, because here you have had a presentation of fundamental concept of statistical inference, a very valuable example of maximum likelihood principle, the definition of what is a sufficient statistics, and a description of how do you build a statistical test. So I think it's a very dense presentation and set of materials. So I hope you will look back at it and then you will come back again with question. Please send question, don't be shy, because I really think it's important to understand if something is not unclear. Oscar is asking, did you sum the residual for each item? Oscar, the answer is yes. It's a weighted sum. It's not a simple sum, but yes, essentially the infit statistic is a weighted sum of the errors across all respondents. And if that is too big, means that that question is not working. Thank you, everyone, and I will see you next time.
Thank you, Carlo.
Thank you.
Thank you very much.
Bye.
Bye-bye.
Ciao, ciao.
Bye-bye.
Bye,
Bye,
everyone.
everyone.
Thank you. Ciao.